Thanks, Ranko. Hi, everyone. Today I'll present the work that I've been doing with Nina Hatch and collaborators at the University of Nottingham. I would like to thank the organizers for making this amazing conference possible and for giving me this opportunity of showing you my work. Well, in this background image, there is a high Z galaxy cluster, and we can see that there are many red galaxies, and these red galaxies pose a challenge to our understanding of galaxy evolution. But why? There are many studies about low Z galaxy clusters. For example, this well-known paper of Peng 2010, in which they correlate red fractions with overdensities and galaxies masses. People also correlate densities with ages, morphologies, star formation rates, metallicities, stellar masses, and colors. And people also study quenching timescales that suggest that galaxies quench after 4 to 6 gigayears after they enter the clusters. However, there are many major clusters at redshift 1.5. And this suggests that quenching timescales must evolve. And when people estimate the ages of these galaxies, it seems they are old. I think Crystal Webby will talk more about that later. And well, but how can we have lots of recently quenched galaxies apparently having old stellar populations? Well, maybe this is related to how quenching timescales are estimated. People use the fraction of excess quenched galaxies in the clusters and the field to estimate these timescales. They are saying that field galaxies are progenitors of cluster galaxies at redshift 0, but maybe this is not true because pre-processing could be going on, and also protocluster galaxies can be different. They can have different stellar mass functions and different halos. So in this work, what we do is to compare protocluster or infall galaxies. It's the same thing here because galaxies that are falling the cluster main halo at redshift 1 will be cluster galaxies at redshift 0. But we are going to compare these galaxies with galaxies in the cluster main halo and in the field. What we do to do that, we use the GOGREEN data. I would like to thank the GOGREEN team for making this amazing data public and making this work possible. What we do is to use the 15 most massive galaxy clusters with redshift ranges between 0.85 and 1.5. As Michael and Veronica mentioned, we can use the UVJ diagram to classify galaxies between passive and star forming. And that's what we do. We also classify galaxies in 3 different environments, which is cluster galaxies, which are galaxies that are inside the redshift of the cluster and also inside one video radius. Infall galaxies are also in the redshift of the cluster. However, they are between 1 and 3 video radii. Control galaxies are outside the redshifts of the clusters and outside 1 megaparsec. Now that we have defined these 3 environments, what we do is the stellar mass functions for each of them and also galaxy type fractions. As we can see here, when we compare the quiescent fraction of the infall, it is very different from the control, mainly in the high mass end. It seems that this infall region has more massive quiescent galaxies. And when we compare this quiescent fraction of the infall with the clusters, it seems that the clusters have more low mass quiescent galaxies. So it seems that there is a mass dependency here. So to try to understand this better, what we do is to estimate the quenched fraction excess. People already mentioned this, but it's the fraction of quiescent galaxies in one environment minus the quiescent fraction of another environment divided by the star forming fraction of the environment 1. And then what we see here is that there is a mass dependency here, and it is in agreement with Vanderburg 2010, 2020. And then it means that even using a different technique, we have the same results. So now that we trust our technique, what we do is to include the infall sample. So when we compare the quenched fraction excess of the cluster with the infall, we can see here that satellite quenching is not mass dependent. And these figures, the orange curve and the purple curves, they are very different. So field cannot be used as a proxy for infall when estimating QFEs and then quenching timescales. Another way to see it is using this figure here, in which we can see the fraction of quiescent galaxies of the cluster and infall divided by the cluster. And the main point here is that it seems that most of the galaxies quenched prior to entering the cluster in this mass range that we are considering, mostly in the high mass end. We also compare the infall and control samples, and we can see that the infall sample has more massive quiescent galaxies compared to the field. It's important to say here that this is not an evolutionary sequence. We are comparing them, but field galaxies will not become protocluster galaxies. Here is the QFE for all the cases. So basically the purple line, which is what people generally consider as the QFE, is a combination of the orange line and the green line. So the cluster, the infall sample is different from the control sample. And now we explore why this is happening. So to do that, we investigate the environment around massive galaxies in the field and also in the infall. We also estimate the number of satellites around random points to statistically estimate contaminants. And then here we have number of galaxies per area per central galaxies as a function of distance from the central galaxy. In the green, we can see the infall, and in blue, the field. What we do is to decrease the dark points by the light points because they are representing here the contaminants. And then we have this third panel. And what we found is that protocluster galaxies have 3 times more satellites than the field. Then we fit a Val-Franco-White profile for each of them. And then we estimate the RS, which is the scale radius, which is proportional proportional to the number of satellites and also proportional to halo mass. And this is the first observational detection that halo mass function protoclusters is top heavy. Okay, so what is going on there? Maybe pre-processing groups are falling inside the cluster in this infall region. They are falling in the cluster main halo, and galaxies could be interacting inside these groups and also interacting with the environment. However, pre-processing cannot explain why we have an excess of massive quiescent galaxies in this infall region. So there is this scenario here, which is called by halo quenching model proposed by Ducker and Berbo in 2006, in which they say that it could be that infall intergalactic medium could be shock heated in the outskirts of halos above a critical mass. So here in redshift 1, these massive halos could be hot enough to stop this gas infall. In the end, we found that protocluster galaxies are different from the control and cluster galaxies. And this has some implications. For example, quenching timescales using field are wrong, and also environmental quenching is independent of stellar mass. And as we can see here in this figure, most quenching happened prior to entering the cluster. We also investigated the environment around massive, thanks Ranko. We also investigated the environment around massive galaxies in the cluster, in the infall region, and also in the field. And what we found is that massive protocluster galaxies are surrounded by 3 times more satellites. And with that, we infer that protocluster region contains a top-heavy halo mass function compared to the field. That's it. I would like to thank you again for this opportunity and for your attention. So if you have any questions, I will be happy to answer.